Welcome to This Explainer. As future environmental scientists and engineers, you're going to be dealing with massive spreadsheets of chemical emissions. If you've ever wondered how on earth to turn that data into actual, actionable sustainability policies, you are in the perfect place. Today, we're mastering the third critical phase of life cycle assessment, Life Cycle Impact Assessment, or LCIA. Think about it. If I hand you a raw data sheet showing 5 kilograms of methane, 20 kilograms of sulfur dioxide, and 150 liters of wastewater, you really can't make a sustainability decision from that alone, right? Like, is that a lot? Is it a little? Is it harming the water, the air, or human health? Raw inventory flows are just numbers. They don't tell a story, and more importantly, they don't give you a clear path forward for real-world design or policymaking. So here is our roadmap for today. We'll move from raw data to impact, walk through the 4 steps of LCIA, define our common environmental impact categories, distinguish between midpoint versus endpoint indicators, compare major LCIA methods, and finally look at interpreting the final results. Let's kick things off with part 1, from raw data to impact. The absolutely crucial point here is that raw emissions data, what we call inventory flows in our field, well, they speak a totally different language than policymakers do. A city planner or product designer usually has no idea what the ecological threshold for sulfur dioxide is. LCIA is the tool that bridges that gap. It evaluates those abstract chemical amounts and groups them into tangible issues we actually care about, like human toxicity, climate change, acidification, and eutrophication. Let's see that translation in action. Abstract chemical weights from the life cycle inventory, or LCI, get converted into distinct categorized environmental impacts. Notice how 120 kilograms of CO2 and 5 kilograms of methane are combined and translated into a single metric for climate change. It's no longer just a random list of gases. It becomes a unified measurement of global warming potential. Moving right along to part 2, the 4 steps of LCI. If you're taking notes, these 4 specific steps, classification, characterization, normalization, and weighting, are your framework for how LCIA actually works in practice. This is literally the engine under the hood. It moves from mandatory sorting in the first 2 steps to optional prioritization in the last 2. Understanding this sequence is absolutely vital for you to conduct a robust environmental assessment. The very first thing we do is step 1. Classification. We sort our raw data points into their respective buckets. Imagine you're sorting mail. You grab all the greenhouse gases, like CO2 and methane, and drop them straight into the climate change category. You take sulfur dioxide and nitrogen oxides and toss them into acidification. And notice that some emissions, like nitrogen oxides, can actually be assigned to multiple categories, contributing to both acidification and eutrophication. Step 2 is characterization, and this is crucial because every emission contributes differently once it's in its bucket. You can't just add 1 kilogram of CO2 and 1 kilogram of methane together. They are definitely not equal. Mathematically, just 1 kilogram of methane packs the same global warming punch as about 28 kilograms of CO2. Characterization uses these scientific multipliers to convert different emissions into one common unit, like CO2 equivalents. Steps 3 and 4 are optional, but they are incredibly powerful for communicating with the public. Normalization helps us identify relative importance by comparing our characterized data to a familiar baseline, like the annual emissions of an average European citizen. It just gives you a real sense of scale. Then, weighting lets transparent stakeholders assign priorities. For example, a group might decide that in their arid region, water use gets high importance, while resource depletion gets medium. It is subjective, which is exactly why transparency here is non-negotiable. Now for part 3, common environmental impact categories. This list is basically the core vocabulary of sustainability reporting. You really need to know these by heart. We translate raw inputs into specific metrics. So climate change uses kilograms of CO2 equivalent. Ozone depletion uses CFC11 equivalent. Acidification uses kilograms of SO2 equivalent to measure potential acid rain. We've also got human toxicity, resource depletion for non-renewables, and water use to track freshwater consumption. I want to pause on this specific definition, mostly because it's so often misunderstood by students. Eutrophication. It specifically tracks nutrient pollution. When excess nutrients, measured in phosphite equivalents, run off into water systems, they trigger rapid plant growth, like those harmful algal blooms you hear about on the news. This depletes the oxygen in the water and completely chokes out marine life. So when you see eutrophication in an LCI, just think nutrient overload.
Next up is part 4, midpoint versus endpoint indicators.
This is a vital distinction in environmental science. Midpoint indicators look at the immediate environmental process, right in the middle of the chain. This means measuring the actual greenhouse gas buildup or the acidification of the soil. Endpoint indicators, on the other hand, zoom all the way out to the end of the chain. They measure the ultimate damage done to our broad areas of protection: human health, ecosystem quality, and resource availability. Midpoints offer higher scientific certainty, while endpoints are usually a lot easier for the general public to grasp.
Part 5. Comparing major LCIA methods.
The big takeaway here is that your methodology depends heavily on your location and your project's overall goal. If you're working for the U.S. Environmental Protection Agency, Tracy is optimized for North American conditions. But if you're conducting broad, global research, Recipe is heavily favored because it beautifully integrates both midpoint and endpoint indicators. Meanwhile, in Europe, CML is prized for its scientific consistency, and EF is highly recommended by the European Commission for studying a product's specific environmental footprint.
And finally, Part 6, interpreting the final results.
As an engineer, you're rarely going to find a perfect zero-impact solution. You will constantly face classic trade-offs, which is exactly why LCIA results should never be interpreted using just a single impact category. Think about it. Product A might be great for the climate, but terrible for local water reservoirs. Product B saves water, but pumps way more greenhouse gases into the atmosphere. If you only looked at the carbon footprint, you'd blindly pick Product A and potentially cause a local drought. Ultimately, the data points journey ends at a human choice. The math can really only take you so far. Balancing these complex indicators requires critical thinking about what your specific project values the most. You have to evaluate multiple indicators simultaneously, deeply considering the local context, what the stakeholders prioritize, and what the overarching environmental objectives actually are. So, with the context, stakeholder priorities, and those environmental objectives in mind, the final answer isn't just mathematical. It is entirely up to you. When forced to choose between a warming planet or drying rivers, how will you weigh the data? Which product is actually better? I'll leave you to ponder that as you tackle your next environmental assessment. Keep questioning the data, and we'll see you in the next explainer.